Hi there, this is Professor Barber. I'm providing for you worked exercises of problems similar to some of the problems of your homework assignment. Consider the graphs represented by Graph 1. The set V consists of the elements A, B, C, D. The letter V is to suggest vertices, and the set E, which consists of the sets AB, AC, AD, and CD. The letter E to suggest edges. So graph 1 has 4 vertices, 4 edges, and the vertex starting at A is a degree 3. Now graph 2 is represented by this drawing. It's 4 segments with vertices A, B, C, and D. A and B are connected. That's an edge. So are AC, BC, and CD. The first question posed is, are graphs 1 and 2 equal? And the answer is no. They are not equal. Now, I didn't know this right away. I had to look at it for a little bit. I know that they are not equal because we notice that there is an edge in graph 1 from A to D. So in graph 1, okay, we have an edge. AD is an element of the edge, but in graph 2, no such edge. That is, and let's go ahead and write it, no edge connecting A and D. So we know they're not equal. The second question is, are they isomorphic? And that's a trickily worded question. A better way to word this is, can you build an isomorphism between graphs 1 and 2? You do a quick study of isomorphism's roots, and it means a bijective morphism. So the first thing we need to ask is it bijective? And the answer is yes. You can build a function from graph 1 to graph 2 in which it is 1 to 1 and onto. So for question number 2, okay, we start out with it is bijective, so that's a good start. Now the next thing is, and what I like to do is just make a chart. So I'm going to have a chart for graph 1 and a chart for graph 2. And I list the vertices. So the vertices that I see for graph 1, okay, it's in the set is A, B, C, and D. And graph 2 are the dots, right? And so we can write those A, B, C, D. Now, the key happens with the edges, the numbers of them, and the degrees of the vertices. So on the edges, okay, what we're going to do is see if we can make a one-to-one mapping. We notice that we have AB as an edge for graph 1. We have AC as an edge for graph 1. And we also have CD as an edge for graph 1. Let's see if I can do a similar thing for graph 2. Yeah, I know I forgot one. I'll come back to it in a minute. Okay, from the graph 2, I see that, I do have an AB. And what else do I have that I want? I have an AC, and I even have a CD. Okay, the issue happens when I look at this and realize that I have an edge AD in graph 1 that I don't have in graph 2, but in graph 2 I have BC. And so we could rename the vertices to make them be a better fit. And the one thing that's left to do is count the degrees of the edges. So if we go to the first graph, I have A. So the degree of A, here I'm running out of space. The degree at A is 3. Let's look at the next one. The degree at B, none. Oh, well, 1 by itself. I'm sorry, that was silly of me. And then we look at the degree at C, and I notice I've got 2 of them. Right, please. And the degree at D, and it happens twice, so that's also. So I've got a 3, 1, 2, 2. Now let's look at my drawings here. So I want to look at the degrees of each of those vertices. So degree at A is 2. That doesn't match, but maybe there's one we could match it to. Degree at B, how many edges are coming out of the vertex? That's 2. Degree at 3 is 3. We've got 3 edges coming out. And degree at D is just 1. So look at this. We have bijective behavior between the vertices. We have edges that do the same thing and the degrees that correspond. So in fact, these two graphs are isomorphic. Draw a planar graph representation of a square pyramid. How many vertices, edges, and faces does it have? The first thing I need is a representation or a drawing of a square pyramid. And so here I have one. Let's note that with a square pyramid, the base is a square, and the 4 sides around it are triangles. To get a planar representation, the idea is to look at the graph from the top down, and when we do that, there's several different ways to do this, but I'm going to use the square for the base, looking from the top to bottom. I'll place a dot for the apex where the 4 triangles meet, and the edges that signify the 4 triangles that stem from the base of the square. So the question then is, how many edges, faces, and vertices does it have? Isn't it a lot easier to count them on the planar graph? From here we see the vertices. Those are the dots, and I see 5. Now faces, those are the surfaces. And again, looking at the planar graph, I only see 4, but remember that the square is at the bottom, so it's actually 5. So we have vertices and faces. What else do we need? Oh, edges. Okay, so edges are the lines that join them together. You can count them from the actual square pyramid or the planar representation, and when we do that, you see 8 edges. 1, 2, 3, 4, 5, 6, 7, 8. I put check marks on them so I can count them off. Explain why it is or it is not possible to walk through every doorway exactly once. If so, in which room or rooms must you begin and end the tour? And B, explain why it is or it is not possible to visit each room exactly once. So, I'm going to make a graph using vertices and edges, and in doing so, I'm going to let vertices, that's the little dots, represent rooms, and edges represent the connecting doorways. Just to be different, let me go ahead and say I'm going to make my drawing A, B, C, D. Notice that D is outside and I'm still letting that be a room. And now looking at my drawing that's provided, I notice that there is a doorway from A to B. So that's an edge. I also notice that there is a doorway from A to C. There is a doorway from C to B. So there we have a cycle or circuit. We have a doorway to get from A to the outside. Can we get from C to D? Yes, not directly, but we can get from C to D. And you can do it 2 different ways because there are 2 exits out of the C room, so I'll just draw another path. Okay, so that's my drawing representation of the room. Now the question is it possible to walk through each doorway exactly once? And we're going to let the doorway, what was it? The doorway is represented by the edges. So can we hit the edges just once? I'm going to do something here. I'm going to count the degrees. And I notice that at C, there's 4 edges coming out of it, so that's even. That's one even. At D, there's 3 edges coming out, so that's odd. At A, there's 3 edges coming out, so that's also odd. And at B, there's 2 coming out, so that's even. So we have 2 odd numbered edges. And we know from Euler's theorem that you have an actual Euler's path if you have exactly 2 odd vertices. And so A, yes, it is possible. And that's because of Euler's theorem. And we begin at either odd vertex, VR, either odd vertex. And of course it says go through each doorway exactly once, which means you need to hit each edge exactly once. Try them. I'll start at D. I can go from D roundabout to C, then to B, then to A, then to C, back to D, and then to A. I hit each edge only once. Hit a couple of the vertices multiple times, but it worked. Now let's go to B. Why is it possible or is not possible to visit each room exactly once? This is a Hamilton path question, and with a Hamilton path question, our concern is, can we go to room A, B, C, and D one time without having to visit any of the other rooms? You can make a path and see that that's possible. I can go from A, D, C, B, A, B, C, D, and so that's 2 paths that work. So yep, it's possible.